Hello, this will be a demonstration of proposition 22 from book 3 of Euclid's Elements, which states that the opposite angles of a quadrilateral in a circle, or in other words, the opposite angles of a cyclic quadrilateral, add up to two right angles. All we are given is the circle A, B, C, D. That would look something like this. Be like that. And inside the circle ABCD, we have the quadrilateral ABCD. And what we have set out to prove is that the opposite angles in this quadrilateral are equal. In that case, that would be the angle ABC plus the angle ADC. Those two angles added together equal two right angles. And similarly, angle BCD plus angle BAD also add up to two right angles. We begin proving this by drawing the straight lines AC and BD. This is simply by postulate 1. Now, by proposition 132 that the interior angles of any triangle add up to two right angles, we can say that in the triangle ABC, the angle CAB plus the angle ABC plus the angle BCA add up to two right angles. So that would be angle BAC plus angle ABC plus angle BCA, all in this triangle ABC. All three of those angles add up to two right angles. Now, from the previous proposition, 321, we can see in the same segment, we have the angles CDB and the angle CAB. So those would be the angles here in the whole segment BADC. So that whole segment right there. And we have the two angles in it, BAC and BDC. And we know that in the same segment, angles are equal to each other. And so we can say that the angle CDB is equal to the angle CAB. Similarly, we can say that the angle ADB and the angle ACB are also equal to each other. So that would be, give me one moment. There it is. In the segment ADCB, so that whole segment right there, we have the two angles inside of it, ADC and ACB. And being in the same segment, we know that they're equal. Again, that's proposition 321. And if we add these equals to each other, we know by common notion 2 that the sums will be equal. And so the angle CAB plus the angle ACB must equal the angle CDB plus the angle ADB. Now if we look, we see that the angle CDB plus the angle ADB add up to the whole angle CDA, so that we can say that the angle CDA, or the angle ADC, equals the angle CAB plus the angle ACB. Now again, adding equals to equals, if we add the angle ABC on both sides, we see that the angle ADC plus the angle ABC equals the angle CAB plus the angle ACB plus the angle ABC. Again, that's simply common notion 2. And in the second step, we showed that by proposition 132 that angle CAB plus angle ACB plus angle ABC equals two right angles. And so by common notion 1, we can say that the angles ADC plus the angle ABC equal two right angles. All right, so we've shown that the opposite angles here, ADC plus the angle ABC, these two angles right here add up to two right angles. Now, we can prove in a similar way that the other opposite angles, that is the angle BAD plus the angle BCD, also add up to two right angles. Now, this being what we have set out to prove, that the angle ABC plus the angle ADC equals two right angles, and also the angle BAD plus the angle BCD equal two right angles, we have shown this is the case, and therefore we are done with the proposition, therefore, etc., Q, E, D. Nothing to say about this proposition. I think it's quite straightforward. I hope I was able to make it more straightforward, of course. So I will simply end the video here and move on to 323.